Let's talk about vectors. Now, most people, I've discovered over the years, most people in grade 11 love vectors so much, they can't wait for me to bring them up again in grade 12. However, well, I may have lied about that. Most people hate vectors. Grade 11. But I will tell you this, that I'm going to make things a whole lot simpler for you. Okay? I don't know. I got to look ahead and see how far we are. Yeah, we'll see. We'll see. Yeah, I know Thursday is post-secondary, right? Okay, so I've only got 4 days a week. Yeah, I can't see us being ready for tests this week. Is that right? Okay, we'll see. Jesse? We had a work grade. I don't remember. Look on Schoology. Okay, let's talk about vectors. Okay, so I promise you that things will get a whole lot easier. Okay? Pardon me? I'm not going to lie. Okay? But the first thing we need to do is have a look at, if I can find my textbook, here it is here. Let's have a quick look here at, yeah, it does kind of look like me, doesn't it? It does kind of look like me. Let's quickly grab page 79 in the book here. Okay? I'm just going to, 79, just going to quickly go through this here. Nope, just listen. All right, so on page 79, vectors in 2 dimensions. Now, we've talked about vectors. Basically, I'm going to, in the next 5-10 minutes, tell you everything that you learned in grade 11, right? So in order to extend our study of motion to 2 dimensions, we first need to describe the processes involved in manipulating vectors. The 2-dimensional planes directions will be referred to as x and y. Positive y will be in the upward direction, positive x will be to the right, as you probably already know. Notice that the 2 directions are at 90 degrees to each other and are referred to as an orthogonal system. And math professors love that phrase, orthogonal, and it just means 90 degrees. Vectors are quantities that possess both magnitude and direction. There you go, right? Oh, yeah. The direction element of the vector is represented by an arrow, where the beginning of the arrow is termed the tail and the end of the arrow is the head. Or the tip, I guess. To specify the angle of the vector, we use the compass system north, south, east, and west, or the up, down, right, and left directions, along with an angle. It's best to keep the angle between 0 and 90 for future trigonometric calculations. Notice in figure 3.1 that the direction of the vector can be specified by 2 different angles, and these angles are complementary, which means what? Add up to 90, and thus, oh, there it is there, and thus add up to 90 degrees, okay? So you notice that there's a few sort of examples there. In the book. So the one on the right there is like this, and it's written as east 30 north, right? East 30 north, or it could also be written the other way like this, and that would be north 60 east. You guys remember all that? Okay. The one on the left there, they have U's and L's, which you will hardly ever see. In fact, I think we could probably almost ignore it. Okay, up 30 left, left 60 right, up. I would just basically ignore that. The one in D there shows west 60 south and south 30 west. Now you also might remember the other system that's not listed there, where north is listed at 0, east is listed at 90, 180, and 270. Do you remember that? Yes, we did. Okay. Where the angle is measured from north and you go clockwise, and that is referred to as the bearing method, and it's actually what pilots and people that captain ships and that kind of thing actually use. Okay? Aye, Captain. Flip to page 80. Adding vectors. Having learned to add from an early age, we're used to the meaning of the plus sign. For scalar quantities, there's no debate as to the final answer. 4 plus 3 always equals 7. But if we use vector quantities, the answer 7 is obtained only if the 2 vectors are collinear. There's another math professor's word, collinear, which simply means on the same line or in the same direction. Collinear. Otherwise, angles anywhere from, or values anywhere from -1 to plus 7 are all possible, depending upon the angle between the vectors. In figure 3.2, you can see that when the 2 vectors point in opposite directions, the total will be a minimum. The closer the 2 vectors are to being collinear, the closer their sum will be to a maximum. So you can see there in A, they got 4 plus 3 is 7, tip to tail. In B there, where 3 is down to the right, they got 4 to the right, 3 down at about a southeast sort of angle. Hello? Sure. Now, okay, so as I was saying there, we're talking about vector addition there on page 80. Blah, blah, blah. We know that you have to add them. When you put vectors to add them, how do we arrange them? Tip to tail. What's the answer called? The resultant. Remember, the new villain? In the book here, they show the resultants with like a double line kind of thing. Okay? Here's where we're going to get into the new stuff. On page 81. Okay? You'll be good. You'll be good. Okay? You might recall from some of the stuff that we did last year, you might recall there was like a force up like this, and then there was an FH like this, and there's an FV. Do you remember kind of sort of that kind of stuff? And I may have used the word components. Okay? And basically what I've done is I've introduced you to vector components in grade 11. I just didn't make a big deal about it. Today I'm going to make a big deal about it. Okay? So, on page 80 there, and you can jot this down or you can just watch kind of thing too if you like. It's entirely up to you. In grade 11, we added 2 types of vector ones. If it was at right angles like that, we placed them tip to tail and we used Pythagoras, a squared equals b squared plus c squared. If the vectors were not at right angles, then we had to settle for a scale drawing. And the problem with scale drawings is that they're not 100% accurate, are they? Right? So it would be nice if there was a... Justin, why are you drawing in my book? Oh. Trying to shoot just the smarty pants. Okay? So that's what I'm going to show you today is how to add vectors not at right angles. Okay. So now this is an example from the book. Now what do you guys have? You got a handout last time, right? It was just this thing, right? Right. Okay. So if you were to do this, then you would too, in grade 11, you would have to, there's vector 1, there's vector 2, there's vector 3, and then the resultant is there, and you have to measure it using your scale and go through all that stuff, right? Not very accurate, Calvin, right? Okay, here's how to do it by components, okay? Now, so what we're looking at here is page 81. Okay, bottom of page 81. A student runs to school covering a distance of 0.5 kilometers in a direction given by north 20 east, as measured from the starting point. She then trudges over to a friend's house, 0.3 kilometers away due west from the school. Finally, the 2 friends go off to the mall, 0.8 kilometers away in a direction given by west 50 south from the friend's house. What is the total displacement of the sister? And if you flip the page over to page 82, you'll see the diagram that was on the previous page. Okay, that's the long and hard way. The easy way is to do it this way. Okay, the easy way is to do it this way, and it's by components. Okay, so let me just see what my next page here is. Okay, so what I would like you to do is, this is the first vector here. This is, again, we're looking at 0.5 kilometers in direction of north 20 east. So 0.5 kilometers at north 20 east. What we do is we break down our vector into components, and I'm going to call this vector 1. And you've got this part, and you've got this part. And the idea behind components is that you break it down into vertical and horizontal components. So I'm going to call this one V1X, and I'm going to call this one V1Y. V1Y is the vertical component of V1. It's the vertical component. It's how much that vector goes up. Okay? Is the number going to be less than 0.5? Like if V1, if this length right here is 0.5, V1 is 0.5, is V1Y going to be less than 0.5 or more than 0.5, or is it going to be equal to 0.5? It has to be less. It's always going to be less, right? The hypotenuse is always less. And V1X is the horizontal component. So it's really how much of this V1 is up and how much is over to the right. Okay? And when you calculate them, Riley, then we can add and subtract after that. Okay? So here's what I would like you to do. I would like you to jot, well, I called it D1, sorry, instead of B1, displacement 1, right? So D1 is simply, guys, you really need to listen, okay? Okay, I understand. I understand. D1 is 0.5 at north 20 east. Okay, so breaking it into components, I need to find out what D1x is. Now, Riley, is D1x, is it opposite or is it adjacent to the 20 degrees? It is opposite. So which one of the three trigs has opposite in it? Actually, tan does too, right? But which one has, we already know the hypotenuse, right? This is the hypotenuse, this is the opposite, and this one is the adjacent. So which one has opposite and hypotenuse? And as Troy has pointed out, it's the sine. So in this case, D1x is 0.5 sine 20. And I maybe should just clarify that right above it. Sine theta is opposite over hypotenuse, right? So that means that opposite is going to be hypotenuse times sine theta. Is it always going to be sine? Is the x always going to be sine? No. Up to you, Carly. You got to start deciding that. Yeah, I know it didn't arrive there yet. I apologize. Okay? The x is not always going to be the sine. Okay? You'll see other ones where it's the cos. So d1x is equal to 0.17. This distance from there to there is 0.17. Okay? Then we use the same thinking to find the y. The y is adjacent and hypotenuse, and you might remember that cosine theta is adjacent over hypotenuse, which means that adjacent is equal to hypotenuse times cosine theta, or 0.5 cos theta. Eventually, you probably don't need to be writing down these steps here, right? You should be able to just see, okay, it's opposite. D1y is going to be 0.5 cos 20. Or if it's opposite, sorry, it'd be D1x is 0.5 sine 20. All you really need to show me is those two typed steps, okay? This is just for people that are a little bit confused here. All I really need to see is those two things. So what I've done is I've taken that vector and I've broken it into components, okay? It's similar to like a color being made up of, you know, the primary colors, right? Every color can be made up of, you take 3 primary colors and you mix them in a certain ratio. Same idea, right? Except here you're breaking it into 2 parts, the x and the y. Now, I suppose there could be, if there was a vector that was in 3 dimensions, right? There would be the x component, there'd be the y component, and then there'd be this one, which is the z component, a 3-dimensional vector. Okay, which is certainly possible. We won't be getting too much into that. So I've broken that vector down into its x and y components. Okay? In this particular example, did I go too fast? Okay. I'll pop. The second vector here is 0.3 kilometers away due west. Okay, so this one's a little bit different because, Darren, it's straight west, Troy. Straight west. Chris, you need to put the phone away, so I don't have to re-explain this to you in a day. I don't want to. Listen now, please. Okay? When a vector is not at an angle, okay, like D2 is due west, does it have a vertical component? Does it go up and down? No. So the D2y, the y component is simply 0. There's no up and down. There's no up and down. Because D2 is just equal to 0.3, because it's west, well then D2x is simply minus 0.3. I've still broken it into components, it just doesn't have a y component. All right? Good? The third vector is down and to the left. Now, did you notice here, actually, I forgot to mention this. Did you notice that D2x is actually equal to minus 0.3? Why is it minus? Because it's to the left, okay? That's important. That's important. Okay, now D3 is equal to 0.8 kilometers. And the direction for that 0.8 kilometers is a direction of west 50 south. So you have to draw the vector itself here. Does this little drawing have to be a scale drawing? No, just a little sketch. Little sketch. So we got west 50 south, D3 is equal to 0.8. D3x is adjacent, so in this particular case, the x is the cosine one. So there you can see the x is not always sine. There's no rule to follow there. So D3x is, now why is it minus 0.8 cos 50? Because same as the last one, it's left, right? So D3x is minus 0.51. D3y is also minus. Why is this one minus? It's down, so minus 0.8 sine 50. If the x is the cos, is the y going to have to be the sine? Like, you're always going to use a sine and a cos, or a cos and a sine? You have to, right? Because one's going to be opposite and one's going to be adjacent. So one will be cos and one will be sine, and they'll always be the opposite. Right? So D3y is equal to minus 0.8 sine 50. In this case, minus 0.65. Now, I'll pause for a second because I know you're jotting that down. Now, I've taken all three vectors. I've broken them into components. What now does your instinct tell you that you should do with those components? Got any? Add them together? Like add all 6 together, Carly? We're trying to add these 3 vectors together. The next step is nice and simple. You simply add all the x components together. Add all the x components together. And I've made it look complicated with subscripts. Let me just explain. Rx, x component of the resultant, is equal to the x component of displacement 1 plus the x component of displacement 2 plus the x component of displacement 3. In other words, add all the x components that you just found. Is it important with the plus and minus? Absolutely. So 0.17 plus a minus 0.3 plus a minus 0.51, and you get an Rx of minus 0.64. The x component of the resultant is minus 0.64. So I have 3 vectors that I'm trying to add. This one here, D1, D2, and D3. I could add them by scale drawing. I don't want to do that anymore. Okay? So I break them into components. I do this. Right? I break them into components, which is what we did over these 3 pages here. I did my D1x, my D1y, my D2x, my D2y, my D3x, my D3y, and then I add all the x's together. Oh, absolutely. It's easy. You add all the x's together, call it Rx. You add all the y's together, call it Ry. And what do you get? You get the components of the resultant, components of the answer. So basically, you take the vectors, you pull them apart, and then put them back together again. You pull them apart, and you put them back together again. Okay? You then draw this picture here. Rx is minus 0.64. Ry is minus 0.14. Pardon me, Troy? Well, because wouldn't you agree that this would blow a grade 11 student's mind? Yes, okay? So you need to understand how vectors work and scale drawing and all that kind of stuff. So, okay? Now, am I done yet? I've got my Rx and my Ry. Now what do I have to do? Well, sort of, right? I'm really trying to find this thing here. Are these always going to be 90 degrees to each other? Oh yeah, absolutely. They have to be. They're the x and y components. They're vertical and horizontal. They're always going to be 90 degrees, which means we can always use our old friend Pythagoras to solve it. Okay? So now you simply go r squared is equal to rx squared plus ry squared. Square them, solve 0.66 kilometers. Okay? It looks complicated, but is it? No. It's just made made to look complicated, right? The subscript's got to be all sort of nice and everything, but it's not a complicated thing to do. Okay? So you find the resultant by Pythagoras. Is this always going to be tangent, Calvin? Maybe you should stop talking to Darren and pay attention then. Because I don't want to explain this to you later. I'll say go talk to Darren because that's what you were doing. Is it always going to be tangent? The answer is yes, because tangent is always opposite and adjacent. Am I always going to have opposite and adjacent? Yep. Now, could I use sine and cos? Sure, because I just found the hypotenuse. But generally, we like to use ones that we already know. So we're going to use tangent here, and we get 12 degrees, and that's going to be west 12 degrees south. Okay? Will this work for more than 3 vectors? We'll get to that. Will it work for more than 3 vectors? Absolutely. 7, 8, 9, 100, I don't care. Any number will work, right? Just break them into components, add them together. It will work. Okay, that's the other beauty of this. Because really, a scale drawing, once you get up to 3, 4, 5, not very accurate at all. Really inaccurate. Let me show you it to you visually. Here's what's happening. Okay? All right. I'm going to take A. There's A. I'm going to add vectors A, B, and C together. Okay? To do that, I'm going to go A, B, and I'm going to run out of room, aren't I? So I'm going to go like this. A, B, C. Where's the resultant? Okay, there's the resultant, right? Watch this. Here are the components, right? There's AX, BX. I say there's BX, get over there. You dirty dog. CX, now where should I put the green one? Right there, right? Okay, which makes the resultant from there to there, right? I take the y's, there's AY. I won't go over farther than that. Okay, BY, CY, which is oddly enough in green. Okay, the resultant is from there to there. I've broken them into resultants. I've added them together. Now, when I take this guy here, and I take this one here, and I add them tip to tail, what do I get? And there's my resultant. Is that resultant the same as that one? It's close enough, right? Yeah. Okay, so what are the steps? What are the steps? You might want to write down the steps. Break the vectors down into components, right? I like to call them X and Y components. X for horizontal, Y for vertical. If you want to call them H and V, you can. Are you going to jot these down, Colin? That is not true. So break the vectors down into components. Next step, add all X components. Right? Add up all the X components. Next step, add all Y components. If there were Z components, you'd have to do that too. Z's? No. Some foreshadowing for next year when you take 13.146, Introduction to Linear Algebra with Professor Quackenbush. Yeah. Seriously. Once I've got my X and Y components added together, what do I do? Well, let's say redraw with Rx and Ry, right? Like redraw the picture. Like that. Are you always going to have a right triangle? Yes. Solve for R and theta. Right? Those are the steps. Right? The details might be a little bit confusing and everything, right? But it's going to be the same steps all the time, Darren.